So let's do chapter 29. Chapter 29, in a way, I don't know, this is one of my favorite topics to cover this semester. It isn't that hard, but it can take just a little hurdle to get over right at the start. And once you get it, and it's not really mathematically intensive or anything like that. It's just conceptually a little tricky right at the start, all right? So the entire chapter is focused on this idea of electromagnetic induction, which is described by something known as Faraday's law. Think of that as the mathematical treatment of the concept of electromagnetic induction. But hiding inside of Faraday's law is a new concept, which is called magnetic flux. Ooh, I need another arrow. Can it squeeze through there? Oh, there we go. Okay? So we're going to start with the idea of magnetic flux, which, since we've done electric flux, is really the same thing. It's really no different at all. It is a measurement of how much magnetic field is passing through a given area. And I want to point out that our area this time, if you look in the diagrams down below, we're going to be a little bit more physical and literal when it comes to magnetic flux compared to the way we were with electric flux, because the applications that are involved, they're impacted mostly by like real circuit elements. Things are going to happen in physical loops of wire that didn't happen when it came to changes in electric flux. So instead of having to imagine like these weird imaginary regions of space where electric field is passing through, you can still do that, but we're going to focus a whole lot more on literal regions of space that are specified by something like a physical loop of wire, okay? So magnetic flux has the exact same equation as what we had for electric flux, except our subscript is different. And as long as we have, say, a regular area and uniform field, like in the descriptions below, it simplifies to just the magnetic field dotted with the area vector. And once again, the area vector is a vector that's perpendicular to the area defined by the loop. The magnitude of the area vector is the surface area itself. If we were to expand that out, that's going to be, let's just for completeness, be a cosine theta, where theta is the angle between those two things. And if we make things a little more complicated, as we might do from time to time, so we'll say for non-uniform field, except I can't spell, back up, or odd-shaped area, we could integrate this instead. Same idea in both cases. For most of the examples to get the concepts across, we're going to keep with the left equation, just to make sure things are sort of regular and uniform, and we'll get the idea. And then for more complicated problems like you might see in the homework, you might have shapes that are a little less constant, okay? A measurement of how much magnetic field is passing through the area. So you can see down below, it works just like it did with electric field. If my area, which is defined by a loop of wire, so keep in mind, think of this as a circular loop. It's just you're looking at it edge on, and there's not a whole lot of perspective there. Yeah, it's not the best. But a circular loop of wire, and it's oriented such that the area vector is in the same direction as the magnetic field. In that case, you're going to get maximum flux, the most that can possibly get through. As I begin to tilt that, the theta comes into play until the point where they're at 90 degrees. There is no flux going through because it simply sort of flows past the area that's there, okay? Any questions about this? You've got electric flux. You've got this, right? 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 I'm wondering, huh? Eh? So you say right, you say eh. Right? Yeah, I guess I see that. Your question? Of the area vector? The key is that it could go either way, I think is maybe what you're going at. It's perpendicular, but it could be perpendicular, well, to the right or to the left on that particular loop. It's defined just like we did with the electric flux. We generally say that positive flux is going out. So we'll stick with that convention, although it's really arbitrary. Whatever meets your needs. If you need a negative sign, if you need a positive sign, as long as you specify which direction, it's fine. Okay? Anybody else? Yes?
Real quick, I'm very sorry.
No worries.
magnetic field going through this wire, and is there current running through this wire right now?
There's nothing running through the wire. In fact, it's literally just a loop of wire floating in space magically. Okay? And the magnetic field is coming from something else and just passing through the area defined by that loop of wire. Okay? Anybody else? All right. So let's take this to the next step and start thinking about flux in terms of electromagnetic induction. It turns out that if the magnetic flux is changing, if it's changing and only if it's changing, you get a current that's produced in the circuit. Even if the circuit is completely connected to no source of voltage. So like we had on the previous slides, just a loop of wire floating in space, if the magnetic flux is changing through that wire, current will spontaneously appear in that loop as if from nowhere. Seems a little bit magical. Maybe a little bit. Like, how can we have that happen without, like, some connection to something? I think if you start to think about the things we've learned, the fact that currents produce magnetic fields and magnetic fields cause a force if a charge is moving, and just kind of sit with that for a second. Take those two things into your head. You got it? Maybe you should close your eyes and just dwell on those two concepts. You're like, I can't because they're on the screen, and I won't remember them. So if charges are moving, it produces a magnetic field. And conversely, if charges are already moving and there's a magnetic field there, they feel a force. So think about the charges that exist, say, in this loop of wire. Imagine, let's just go with positive charges since that's our convention. Imagine they're just sitting there. They're not doing anything. They're not moving. And maybe even there's a magnetic field. And it's like, yay, I feel a magnetic field, but nothing's going to happen to me unless I start to move. Okay? So now think like, well, I'm not going to move because I don't want to feel a force. But instead the other thing happens, and the magnetic field starts to change. Okay? You can almost imagine like a magnetic field coming along could make those charges start to move. Got that? Do I need to say that again? Charges are sitting there. If they move on their own for some other reason, then they will feel a force. So maybe if instead of them moving and feeling a force, we can somehow move the magnetic field, which causes a change in flux, and that movement of the field results in the charges moving instead. So it's sort of like an inverse effect from what we were talking about before with a force on moving charges. All right? So maybe it's not quite as magical as it seems. Like these magnetic fields are passing through the charges and they're influencing them. It's not just completely random, you might say. Yeah.
If you were to, like, let's take this first picture here. So if you were to have a magnet face the same orientation, so the North Pole facing the wire, and you move both magnets at the same time.
So two magnets.
So two magnets, and we're moving both of them at the same time in opposite directions. Would that change the flux as well?
If you can move them in such a way to get the effect to cancel out so that it's constant, then there would still be no effect.
Okay.
So if there's multiple fields you're having to look at, you have to look at the total field and how it's changing.
Okay.
Okay? So let's look at these bottom three cases. I want to start in the middle one. Notice there is a bunch of loops of wire that are connected to an ammeter. It's there to just measure the current. You can see that in this middle case, it's 0. Even though there's a magnet nearby, that magnet in this case is not moving. So whatever magnetic field is passing through that coil of wire with all those loops, it's not changing. So nothing is dynamic, nothing is happening. There's no current flowing in the wire, and that's probably exactly what you would expect. You're like, it's not connected to anything anyway. Why would there be current? The thing is, if you go to the left and look at this diagram, notice in this case, that magnet is moving to the right with some velocity. So you might imagine it's getting closer, and the magnetic field that's there is growing into the loop. As it gets closer and closer, there's more and more magnetic field and therefore more magnetic flux through those coils. As long as it keeps moving and there's a change happening, you can see that the meter is reading something. There's a current that's, we would say, induced in the loop. Okay? Yes?
Again, I'm sorry.
You're fine.
If you were to
If we were to push current through the wire, through some other source, we would have two effects we would have to consider. This would still happen, and we'd have to consider that, but simultaneously, you've got current that's making its own magnetic field, and stuff is happening. We're going to see in next chapter that a coil all by itself with changing current is affected by the changing magnetic field through itself, but we don't have to worry about that yet. Okay? So at this point, keep the coil and something making the magnetic field separate. And we'll deal with the combination next chapter. Okay? Notice over on the right, we've just decided to move the magnet the other way. If I move the magnet away, the amount of magnetic field that's passing through that coil is diminishing. There's less that's passing through there. Well, you might expect now, as long as it's changing, you're still going to get a current, but the opposite thing is happening. We might expect the current to be in the other direction. We're going to explain how you can figure out exactly which direction the current is. At this point, I just want you to get the idea, okay? There's a bar magnet. It's moving in relation to the coil. That creates a changing flux, which creates this induced current, okay? Now, notice a couple of definitions there at the start. If there is a current that's produced by this effect through electromagnetic induction, we call that an induced current. It is no different by definition than like current we learned about before. All of those current definitions apply. It's just moving charges. We're just saying like, oh, this current came from this, so we're trying to isolate that so that we know where it came from a little bit better. Keep in mind also, charges can't flow unless there's a potential difference. So if they're flowing, there must be some potential difference in that coil, even if there's not a source of potential difference. We call that the induced voltage, okay? One other thing is happening, and there is also in the coil an induced magnetic field, which we're going to talk about soon. Ooh, see you later slides. Okay? Is everyone still okay with what's happening so far? Your question. Did the current come first or did the voltage come first? Chicken or egg problem.
What if it's a short or what if it's an open circuit?
If it's an open circuit, still nothing is going to happen in the wire. It still has to have a path through which to flow. But voltage or current first, let's just say simultaneously. Anybody else? No? All right. So let's look at Faraday's law of induction, which I have a lot of space here for a very short mathematical law. So we might as well use most of that space. Why not? So the amount of induced voltage is what's described by Faraday's law of induction. And here we use the same symbol as for EMF instead. Sometimes you'll just see this written with a V. Don't get confused by that. I'm just writing it the way that it's typically written in this case. So this is simply the induced voltage. And it's equal to negative the first derivative with respect to time of the magnetic flux. The time rate of change of magnetic flux. If the flux isn't changing, there's no induced voltage. And we could expand this a little bit. If we have multiple loops of wire that are all connected to each other, this exact effect happens on all of them, which means that if I have two loops, I get two loops. Just made me think of Fruit Loops. I haven't eaten Fruit Loops in a long time. Who had Fruit Loops within the last week? Anybody? You're like, what are Fruit Loops? You know, it's a cereal. Some people have it for breakfast. Like, you're too adult for that, aren't you? Who had oatmeal? You had a banana? Yeah. I don't want to hear it. Nobody had Fruit Loops, though, huh? Anybody have Pop-Tarts? Yeah, me too. High five, yeah. Pop-Tarts are the best. Nothing better than Pop-Tarts. My wife hates them and hates that I eat them, but who cares? Let's see. So if you have multiple loops, N is the number of loops, and it's just equal to N times this rate of change of magnetic flux. So for every loop you have, you get the exact same effect over and over and over again. So if I'm trying to generate an induced current, it kind of makes sense to fit as many loops into the space as you can if you want to maximize the amount of current that you're going to get out of this effect. I don't think there's anything terribly difficult with using this particular law. The thing that I want to focus on is that negative sign. Your question first. That's a little hard to say, because if I have, let's say I go back to that first slide and I just have a single circular loop, where does the voltage start and where does it end kind of situation? We're having to step outside of it and think of it as a little more theoretical than anything, because I couldn't, like, where are you going to make those connections? It's continuous. There has to be, at least theoretically, an induced voltage there to get the induced current. Yes?
And then the derived induction, the induced current, is the same as like any other one? Or are we going to get that?
What do you mean?
Like, it's the same as to the base, like, divided by R? And
Yep. Yep. Everything else still applies like we used with currents before. Anyone else? Yeah.
In effect, you can basically get current from Rn, like resistance of the wire, and the flux.
Yeah, totally. Yep. So yeah, we could use this inside of Ohm's law if you wanted to find the current from the potential. Yep. The negative sign. Ooh. How about that? What about the negative sign? The negative sign has a name of its own. And this is the only case I can think of. There might be another one hiding out there somewhere where a negative sign in an equation is its own law. And I feel like that seems generous, don't you think? Like Mr. Lenz here got a law named after him based on this negative sign. Why can't we all have that? You know? Like, I've put negative signs in things before, solving a problem. Haven't you? How many negative signs have you used this semester? Yeah? I bet you've even used some inventive negative signs where you're like, I really need this to be positive, but I got a negative. And you just slide one in there somewhere in the process, and like, nobody's ever going to notice that. Yeah, you've done it, haven't you? Uh-huh. And then some of you who've done it, it kept you up at night a little bit, thinking like, I did something wrong in that problem. I don't really understand how to do that problem. Hope that doesn't come back to haunt me. And alas, it still hasn't, has it? So you really don't care all that much. So this negative sign is known as Lenz's law, and we could write a more extensive statement of this. We could say that the induced magnetic field and current and voltage, all of the induced things are in a direction such that they oppose the change in magnetic flux. The induced things, magnetic field, current, and voltage, are all in a direction, in agreement with each other, such that the change that's happening in magnetic flux is trying to be canceled out. It's opposing the change. It doesn't like the change. It's almost like the loop of wire is a little temperamental in a way. Like it's sitting there and it's maybe there's some magnetic field that's passing through it. It's like, I love the flow of this magnetic field. And then all of a sudden you decide to remove the magnet a little bit and it's like, And it does whatever it can to try to keep the magnetic field like it was before. The thing is, it's not just temperamental, is like, I don't know, it adapts very quickly to the new thing. So it's like if the magnetic field goes down a little bit, like it'll try to generate its own magnetic field to get it back to where it was, quickly realize that it has no source of voltage and can't, and then quickly become accustomed to the new magnetic field. It's like, okay, this new one is fine. And then you change it a little more and it's back to, okay, it's fine. Oh, that's not so bad. And as long as you keep changing it, it'll get upset, oppose it, and adapt. Okay? So, how does that work out in practice? We've got the same two diagrams from the first slide. The one on the left and the one on the right from the first slide where we have a magnet that's moving toward and away from a loop of wire. So let's look at the example on the left where I have a magnet with the north end pointing to the right and it's approaching the coil. I kind of hate this diagram in some instance. I want you to keep in mind that all of this stuff that they've drawn with the loop itself, including this like ghostly bar magnet and the current and the field lines, none of that is there at the start. Okay? So in other words, if the velocity is 0, everything that's associated with the loop just goes away. It vanishes. It only appears when there's a velocity of that magnet approaching. Okay? So think of it in 2 steps if you have to. Imagine it not there, and then when I add a velocity, all of a sudden all that stuff happens. So if you think of the magnetic field as coming out of the north end of the magnet and it passing through the loop to the right, that's what's growing as the magnet approaches. So maybe the loop started with no magnetic field, and now all of a sudden all these field lines that are going to the right are increasing in strength as the magnet approaches. Okay? So maybe this thing started with no magnetic field and it liked it that way, and now this magnetic field is growing through it. It's going to do whatever it takes to try to cancel it out. It's going to ultimately fail, but it's going to try. So what it does is creates a magnetic field the opposite direction. This is what we call the induced magnetic field because it's trying to cancel out the lines that are growing through it. Okay? Once we figure out the direction of the induced magnetic field through the center, which is represented by that ghostly-like bar magnet that's there, point your thumb in the direction of the North Pole. A few more of you. More of you. More of you. Thank you. That's good. As soon as I turn around, you're all going to quit, right? Okay, you kept it that way. Now my fingers curl in the direction of the induced current around that loop of wire, which you can see is indicated there as well. Okay? So this is really the same right-hand rule we had before. We're just applying it to all the induced things. So let's make a quick note here that this is the direction of B induced in the center of the coil, and that is the direction of I induced. Before questions, let's consider the backwards case and then see if you understand. And if you don't quite yet, you'll ask me. Okay? So what if the magnet gets kind of close and then we decide, like, well, that's enough. Let's take it the opposite direction. Well, at this point, the coil has gotten accustomed to having a certain level of magnetic field passing through it. And now those magnetic field lines are going and shrinking. And it's like, no! Give me my magnetic field back. And it's like, okay, clearly you're not going to, so I'll make my own. So this is being removed, so it says, I'll make one this way, trying to add back what was lost. So the direction of the induced magnetic field this time is that way, and from your right-hand rule, you can get the direction of the current. So this time, our thumb is pointing that direction, and you can see the direction of the induced current is around the top towards you. Got it? Yeah. No? Let me label this real quick, and then I'll turn around once again. Questions, thoughts, comments, complaints. Your question. So if we went to like different parts of the loop and got a voltmeter? Good question. I don't know. I haven't tried it. I might expect that you would end up seeing like the same potential difference as long as you keep it the same distance apart, the same amount. But I don't know 100% for sure. It's a good question. Yeah? Why does this happen? Because nature doesn't like change. I don't think that's a good answer. No. It all is happening based on what we said back here. It's kind of like the field lines that are changing in strength are giving the charges a little shove. Yeah, I can see it kind of is getting there, but maybe not. No? That's all I've got for you right now. We can talk more later, though, if you want to. Yes?
How are the field lines changing in strength? Wouldn't it just be that bar magnet as it's passing through, it's going to
So two things. First of all, let's make sure that we're focused on like some movement. Let's say this moves from like here to here. That's as far as we let it go instead of passing all the way through because that complicates things. As I'm farther from the magnet, the field strength is less. So in other words, a point right there has a stronger magnetic field than a point right there. And now I'm moving the magnet closer, which means that you can think of it in two different directions. The flux is increasing because, well, B is increasing, really, as it gets closer. So in BA cosine theta, B is the one that's changing. Okay? Anybody else? Yeah. Yeah, we can do stuff with this. Yeah, it is. And you may have done stuff with this and not known it, which we'll talk about later. Yeah. Yes, you can. If you change any part of the flux equation, which is exactly what we're going to work through here, you will end up changing the flux. So you could have all components of this changing or any part of it. So on the previous slide, we said just a magnet moving toward or away. In other words, in that particular case, B is changing. We could have a case where maybe there's not a magnet that's moving closer, but perhaps we're generating a magnetic field in some other way by maybe some other coil of wire. And maybe you have a big dial where you're just like, send more current through the wire and create a larger magnetic field. So maybe you have a case like this where I can just change the magnetic field strength in an area. That would also be a change in B and thus induce a current. Notice here they've illustrated a case where we have a decreasing magnetic field. See the line density here compared to the line density there. So in these two cases, the strength of B is decreasing. And I do like this illustration because they show the loop itself like adding in more field lines in the same direction, trying to get back to the density that's over here. And you can see that illustrated. And once again, if magnetic field pointing in that direction is going away, then it induces a magnetic field in the same direction, and the current is according to the curl of your fingers. So I think I should draw a little bit more here and say that that is the direction of B induced, and that is actually what all of these lines are. Those are induced magnetic field lines. But we can go further, and like you said, we can change the area. So think of that in a couple of different ways. Maybe we have some sort of magic loop we can stretch. I don't know where that's happening at, but maybe it's a loop of wire, and we can just go, ooh, I just made it bigger through stretchy wire. Sure, why not? You know, in that case, if this gets bigger, there's more flux, and it'll try to cancel that out. If it gets smaller, there's less flux, and it'll try to cancel that out. But the last one, the effective area, you could think of that as coming into play with theta. If I rotate the loop, well, that's the same thing as essentially decreasing the amount of area or space for the magnetic field to get through. Same idea, same effect. If it's losing flux or gaining flux, it's going to try to counteract that in such a way to try to keep it like it was. All right? So who's got thoughts and questions before I ask you a lot of questions? There's like 10 in a row here or something because it tends to confuse people, and I just want to make sure you've got it. What are you eating? Effective. I see what that is. Those are dried banana chips. It hurts. It just hurts. Yeah, those are terrible. No, don't do that. Please pour them out. That's what's going to happen, right? Okay, I'm going over here now. Oh, all right. So first of all, I'm going to skip this one because, well, look at it. There's no perspective. I can't tell what's happening there. It just confuses people because the drawing is terrible. And let's go to the next one. I'll give you a second to read it and see if you come up with the answer. All of the little X's indicate a magnetic field that's into the screen. Hello, back row people. How are you? It's a high density of you back here today. What's up with that? Ah, you get a free charge back here. That's good. Can't complain about that. One, two, or three? So if that loop, let's say it just moves a little bit to the right, is the amount of magnetic field that's passing through that rectangle changing? No, we're not going to let it go that far. Just as it stays inside the field and moves to the right, the flux is not changing, so there is no induced current. B, A, and theta are all constant. So we could say that d flux dt is equal to 0 in this case. Let's go to another one. What if it starts to leave? If you're not using your mental right-hand rule, then you should be using your physical right-hand rule and trying to sort it out. Oh, I see all the iced drinks, and I really want them. You've got like an iced coffee or something happening right there. You better finish it off, because I really, that was even mean. Like, while I'm still talking, you're like, it's good. What's this? You don't know? Just somebody's drink? Maybe it's your drink. Yeah. You have coffee in there? Yeah. Question.
If you use your left hand, would that be for if you wanted to like move? You're using southpaw?
Let's not go there. I'm afraid there's too many things that could confuse. Unless you want to. Nah. You brought banana chips. I can't help you. That's how this works. So let's see. It's losing flux, right? As it departs the field, it's losing flux. And that loss in flux is into the screen, which means it's going to try to essentially add back in what's missing by inducing a magnetic field in that direction. If that's the case, the right-hand rule tells us that the induced current is going to go around clockwise. Whoops, that's I induced. So you should get a clockwise current there. Is that what you got? Yes? Okay, good. Questions? You're okay? I'm just sneaking up here to try to get rid of those banana chips. I feel like if I just destroy them. Or maybe we could make a deal. When I'm not looking at all, could you remove those from the room?
I'll try my best.
Yeah? Okay. There's a trash can right here. You can just take it right up there and just... And actually, I think we should have like a banana monitor in each class. They just walk around with a trash can and just collect bananas and toss them. That'd be fantastic. We could donate them somewhere, I guess, but we should trade them for something good. If we're going to give them away to somebody, like we should give them something tasty. Yes? Twisted in the middle. Ah. It sounds to me like all the effects would be canceled out, perhaps. Maybe there would never be induced current because of cancellation effects. Yeah. If we had a loop that was twisted, so maybe like an 8, like a figure 8 shaped loop. Yeah. Although you don't necessarily have to Mobius it, because it'd be kind of the same thing. But I think the effects would always be canceled, as far as I can think off the top of my head. Yeah. What about this one? Hey, look at this. There's a weird stray F just kind of hanging out in the corner there. You like that? Look at this. Why is that there? I have no idea. What is that? Yeah, it's the induced current. I like that. That sounds more like it's money related in some way. Some people in the back are just getting your joke. It took them a little while. It kind of transfers back there. You're making more jokes? Yeah. You want to share? I'd love to. What's that? Huh? No? What? No jokes that I can hear? No. All my jokes are not funny. All of them have to be funnier than anything I joke about in here. No? Yeah. I've rubbed off on all of you, right? Now you're making worse jokes than me. Oh, you can make jokes about anything. No? Okay, you're not going to tell me. That's fine. Yeah, I understand. There's a lot of talking down there. I think they're trying to figure it out. It doesn't sound like random chatter. Would you agree? It sounds like thoughtful chatter. Do you have the answer down there? The magnetic field is suddenly increasing while the loop is in the region. It is not going to like that, so it's going to try to cancel out the increase by creating an induced magnetic field the other direction, which gives me an induced current that way. So we're back to counterclockwise. Can I slide through here? Thank you. I appreciate it. You did finish the coffee now, huh? Whoop, did I just take your pen? Or the wire did. My apologies. Next question. How about this one? Here's the magic shrinking loop. We're all getting the right answers? Yeah, maybe, no? Question over here.
So it's going to be losing it, so it's going to try to add it in, is what you're saying?
Yes. Tries to replace what's lost. Oh, you brought lemonade again. Man, you're hurting me. Oh, my apologies. That is clockwise that I drew, isn't it? Thank you. Clockwise. There we go. B induced is adding into the page. Right-hand roll gets us clockwise. I drew it right, but I can't think apparently. How about this one? So yeah, the magnetic field is literally pointing to the left, and you can think of it as the coil is sort of turning into it. So it starts with no flux, and flux is increasing. And then we're going to try to determine the direction of the induced current in the coil before it turns too far, and counterclockwise and clockwise mean opposite things. I believe we're going, which way? What's it going to do? I think it's going to go like this. Yes, no, yes, maybe. So let's see. Think of it like this. I start with a magnetic field that's pointing this direction, and my loop is turning like this. So there's flux going into the loop that direction that's growing. It'll try to counteract that with an induced field the opposite direction. And if that's the case, then we end up with counterclockwise current. A few more of you look a little concerned about that this time. Questions? No? You like it? You got it? Why so much silence then? It's like all of a sudden, like you just want to listen. It's weird. You're freaking me out. Stop it. Talk to each other. I can't take it. How about this? Look at these creepy hands. Look at what's happening here. Wow. These disembodied hands that have apparently just dropped a magnet. We are only going to consider as the magnet is approaching the loop. Don't let it fall all the way through. And we want to compare the magnitude of the induced voltage in these two cases. Remember that capital N in the equation, right? More loops gives me more induced voltage. So 2 is going to have a larger induced voltage than 1. Yeah? So what can you say about the induced currents? This is a trick question. Don't you wish exam problems said that when it were true? But then you could say this is a trick question on a question that's not, but by writing that you made it one. No, don't do that. That sounds terrible, doesn't it? Huh. Maybe I will. would I find the current from the voltage? Yeah, it's gone because you threw them away? Don't believe that for a second. And I also bet that jar really stinks. It's all banana-y on the inside. Oh. Yeah. Any votes out there? So what if I were to do this? Except we're looking at induced things this time. And resistance is resistance. Has the resistance changed? Yeah, it has. If I have twice as much wire, even if the resistance is small, I have twice as much resistance. There's the trick. So this is 2R because I have 2 loops, and this is twice the other one as well. That just means everything cancels out. I still have an induced current, but they're equal to each other instead of there being a proportionality there, okay? So twice the resistance kind of kills the effect in this particular case, all right? Let's see. Is there one more? I think this is the last one, isn't it? No, it's not. There's 2 more, maybe. 2 more. This will be a 2-step problem. You need to think about something from a previous chapter first. Let's start with the direction of the magnetic field being created by the wire. Thumb in the direction of the current. So on the right side of the wire, there's magnetic field that's into the screen. So we could say that which is coming from the wire is like this. Keeping in mind that it's getting weaker the farther I get from the wire, based on chapter 28 stuff, okay? So as it goes away, it's essentially losing flux in that direction, which means it's going to add back in its own magnetic field as it moves in the same direction to try to cancel it out, or not to cancel out the change, and then we're going to get induced current in that direction, okay? B gets weaker as I get farther from the wire. So would that change your answer if the loop goes that direction? In this case, flux isn't changing. If it's staying the same distance from the wire, that's a constant magnetic field that's passing through it, so a constant flux. So there is no induced current in that particular case, right? Let's see. This particular problem I've decided not to do, mostly because it's just way too easy. If you want to do it later yourself, you'll see like, oh, that was just plugging in a couple of numbers and nothing else. Instead, I want to take you to this particular example of a case where we get some induced voltage or induced EMF simply when a conductor is moving. So if you want to think of this as like a particular case of Faraday's law being used, that's good. I'll give you an example of a couple of cases where this does apply in just a minute. Start by taking a look on the top right. On the top right, let's just zoom in on that. We've got a bar of metal that's represented there in the middle by this, and it's moving to the right at some velocity. It's connected somehow like on these metal rails that complete a loop that goes around this way. So maybe you can imagine that as this moves this direction, by some means or other, maybe it's oriented in such a way that gravity's pulling it, which clearly isn't the case here. Maybe someone is manually holding onto it in some way and pulling it to the right. Something is pulling that part of the loop to the right, which is effectively increasing the area that the magnetic field can pass through. If that's happening, there should be an induced current that goes around that area that's growing. Which direction is it going to be? Clockwise or counterclockwise, first of all? We'll use this as more practice. As the bar moves to the right, what's the direction of the current? Clockwise? I like clockwise. Yeah, so as it goes to the right, flux towards you is increasing, so it generates a magnetic field that's that way, which gives us a current that goes like this, okay? Let's take that fact together with an application of Faraday's law and see if we can figure out the magnitude of the induced voltage. So, what we're going to do is start by looking at the velocity. Well, let's give ourselves a little more space. By the way, watching you people use the right-hand rule kind of cracks me up. You all have such a different style. You know, some of you look like you're like at an auction or something. It's like and then you vote. Like, that's the end of it. Some of you, like, reach far away from your body as if it's like an interpretive dance or something. It's like, and then like all of this. And then the rest of you are somewhere in between. But I like it. Just keep that style as you go forward in life. Using the right-hand rule on a daily... No, you're not going to do that. Your question?
Why was the area increasing? Because, like, isn't it when it's passing that bar doesn't, like, change length or anything, right?
The bar doesn't change length, but the area is defined by this space, the space that's defined by this loop. Ooh. So as it moves to the right, that region's growing. Good question. So let's start with the velocity. The velocity we know is dx dt, or d some position coordinate. If we just say to the right is the x direction, we could write it as dx dt. So we could rearrange that and say that dx is v dt, all the way going back to like the first lecture last semester probably. And then we could change that to dA if I multiply it by what? L, right? If dx is a little bit of changing width, then multiplying it by what is L in that diagram will give me dA. So we can write that as v dt times L, and they used a little L in that diagram. So it's the area that's changing here, and we're going to use that equation for the change in area as it moves to the right in Faraday's law. Let's specifically just focus on the magnitude. Since we already figured out the direction of the current, we really don't need anything else. So we'll write that as d flux dt, which is d dt ba cosine theta. What's theta in this particular case? It's 0, right? The area vector, we could define it as toward us, and then the theta is 0, so that's just going to be 1. The magnetic field is constant, and it's the area that's changing. So let's write this as b d dt v. Let's just keep doing it like that. There we go. And then we'll pull out the additional constants that are there. So let's see, if it's moving at a constant velocity, that's bvl, and then I have dt over dt, so that's just gone. And take a look at what's left. The induced magnetic field there, or the induced voltage rather, is given by the field that's there, that's being generated by something else, times how long the bar is that's moving, times how fast it's moving, okay? So if you think about it, there's nothing in that equation that really talks about the rest of this loop. There's nothing there that's left at all. Instead, everything that's there has to do with this piece of metal and the magnetic field that it's passing over, okay? That means that we could take that piece of metal and just separate it out all by itself and let it go through a magnetic field, and there will be an induced potential difference across that piece of metal. If that bothers you a little bit, let's think about it in terms not of Faraday's law, but in terms of the magnetic force, which you remember is QV cross B. And keep in mind, a piece of metal, well, it's full of electrons that are free to move around. So if I pass that piece of metal through a magnetic field, well, those are charges that have a velocity in a magnetic field. They're going to feel a force. So let's think about that just a little bit. Starting with the right-hand rule and considering a positive charge, the velocity is this direction, and the magnetic field is towards you, right? So the direction of the force on a proton would be down, which means that the force on an electron is going to be up. Either way gives you the same thing. Notice we end up with a separation of charge. One end of the conductor becomes negatively charged, the other becomes positively charged. So you can think of it as in terms of F equals QV cross B. You can put it into a circuit and think of it as Faraday's law. You get the exact same result. There's a potential difference across a piece of metal that moves within a magnetic field. And you might think, well, where is that happening? When is there just a piece of metal that happens to move through a magnetic field? I mean, I guess I could take a magnet and throw that chair by the magnet. That would happen, but who in the world cares if there's a potential difference across the chair? And how often does that happen anyway? But can you think of a case where maybe this happens a lot? Yeah? Magnetic strips. That is an application of Faraday's law, but I wouldn't think of it as a piece of moving metal through a magnetic field. It's a little bit different. You're close. Yeah? Yeah, airplanes. This seems like a problem. Airplanes fly through the Earth's magnetic field. So question is this a problem that airplanes need to consider? And to determine whether it's a serious issue, we're just going to use some typical numbers and find out. So let's say that maybe we had an airplane moving at 280 meters per second. I checked, that's a little over 600 miles per hour, so that's about the speed of most commercial jets. And let's say that the tip-to-tip wing size, if we want to go that direction instead of the other, just pick one. We're going to say that that's 70 meters, okay? So let's say a nice big jet is flying through the Earth's magnetic field. In some regions of the Earth, the magnetic field is going to be perpendicular to the wings. In other places, it's not. We're going to see what the maximum possible effect is. So we're going to consider a case where we've got the most possible amount of flux. So B max is going to be 5 times 10 to the minus 5 Tesla, and we will say vertical to give us the maximum effect. So we're considering the worst case scenario just to see if there is a problem, and then we're going to solve this using BVL because we have all of those. If you plug those numbers in, you get kind of a depressing result because after all this hoopla, I don't think I could call that hoopla. We didn't have hoopla. What is hoopla? All of a sudden, it's a very weird-sounding word the more I say it. So after saying that we might need to be concerned about this, you end up with 1 volt across a 70-meter difference. I don't think that's going to be a problem, all right? On the other hand, if we'd gotten a number like, I don't know, 10,000 volts or something, you might have to worry about something where it's like airplane flies and then there's like lightning across the wings that it generates. That would be a concern. We're not going to have to worry about that happening here. There's not going to be a great flow of charge or anything. Okay? Question? What's that? Does the potential depend on the material? No, we're just looking at a conductor. So would it change if I had, say, a semiconductor or something? It should, but I don't know exactly how. Yeah.
Did you say that bottom diagram when we're looking at PVV?
Yep.
Was that to explain, like, kind of in words why there's an induced voltage? What was the...
It's 2 things. It's another way of looking at why there's an induced voltage, but also considering the fact that the equation we ended up with had nothing to do with the remaining part of the loop, the non-moving parts. There's nothing in there related to it, and that explains why. I see another hand somewhere, I thought a minute ago. Maybe your question got answered. Yeah. Do electric trains produce magnetic fields? Sounds like the title of a book or something. It should be a children's book. Do electric trains produce magnetic fields? No, it shouldn't. Where and when? Like the train itself? some, yeah. I don't have that calculation on hand, though. Anytime we have something like that that's metal that's moving through a magnetic field, then, yeah. Yes? I'm sorry? When there's a thunderstorm, then we're looking at two separate effects we'd have to consider together. The Earth's magnetic field itself isn't going to be affected by the thunderstorm, but the question is maybe there would be an additional magnetic field. I can say that there would be when there's lightning strikes because you have a strong motion of current. But when there's not, there's just a potential difference build up and not necessarily an additional magnetic field. Good questions. Yes?
Why do magnets, like a really strong magnet, why would that erase the
It's because of how it's encoded on the permanent magnet that's on the credit card itself. It's been encoded with information magnetically. And like what we had at the end of the last chapter, you can demagnetize things, a ferromagnetic material. If you demagnetize that, you just lost all the information. Sad. Yes? Uh-huh. Yeah. Ooh. I guess we should always say motion relative to what? We have defined it as motion relative to what it's traveling through. But you could say that it's always moving relative to something, which will bring in some more complicated physics. We would have to consider relativistic things in that case. All right, let's see. We did that. We really actually already answered that question, so I'm not going to do that anymore. And that completes 29A. Okay, so that's the first half of this chapter. We've got 20 minutes left. What do you want to do with it? Yeah, that's what I was thinking. Good answers. 29B. I want to do a little bit of 29B. Yeah, some of you are like, what's wrong with my classmates? Like, he just gave us an opportunity to leave. Actually, you really never had that chance. So, don't blame your classmates. Let's see. I want to talk about a couple of things here before we go today. If you think about everything that we've been talking about, changing flux from a magnetic field through a coil of wire, well, if I can produce a current in that way, well, it seems like that might be a pretty good way to just, in general, produce electricity. And that is how it happens. So in this particular case, we're sort of simplifying down greatly the idea of an electric generator. Think of just the ends of two bar magnets that are positioned near each other to create a constant magnetic field that points from north to south pole. And then we're going to take a square loop of wire and turn it using some other force. So think of that as mechanical input. Maybe it's someone that's just, just turning it with their hand. Maybe you've decided to put that with paddles or something so that water can flow over it. Maybe you've decided to connect it to a windmill. All the same idea, right? You have some means of mechanically turning the loop of wire, and that loop of wire sits inside a magnetic field that's already there. If that happens, as long as it keeps turning, there's going to be ever-changing magnetic flux. It's never going to stop changing. So really, this is that loop's worst nightmare, It never gets a chance to adjust. Like every second is different than the second right before that. If that happens, it's going to always produce current. The thing is, the rate of change of magnetic flux changes as it rotates, okay, because of how the area is effectively decreasing, which means we're going to get a change in how much current we get. But also, keep in mind that once it rotates halfway, now we've sort of flipped which side the magnetic field is going into, which means that now as the flux changes, it's changing in the opposite direction. So not only do we have a varying amount of potential that's created, we have a potential that's flipping direction as well. This basic setup is how we produce alternating current. So you could think of it in this case as an alternating induced current, which is kind of cool in a way, all right? We're going to see how this works out using Faraday's law, and then we're going to talk about the next slide, and then we'll be done for today. That was a long search that's been going on for quite a while. I'm sorry to bother you, Siri and Apple servers. My apologies. So let's see. Let's say that this is rotating at that angular velocity, a constant angular velocity, and let's use Faraday's law. Let's see. So let's use the whole form with the negative sign. And we'll change that to BA cosine theta. So theta here is what's changing, and theta is changing because of this angular velocity omega. So if we were to let the starting or initial omega be 0, we could say that omega as a function of time is equal to the starting angle, which we'll let be 0, plus omega times t. So if you remember back to your angular kinematics a little bit, perhaps, last semester, I don't know, I think you probably remember. Angular velocity, think of that as radians per second multiplied by time seconds. You can see we get radians. We get an angle out of that equation. Or, let's see, let's re-express this, and we could say that if we rearrange that, omega is theta over t, or we could rewrite that as d theta dt. Or in other words, d theta is going to be omega dt, and that's what we're going to use in the equation above. Question about those little intermediate aside steps before we go back to Faraday's law. Anything? No? Okay. So back to this thing from above. Let's pull that down here. Let's see. The area, it's just a square loop. That's not changing. The magnetic field is coming externally, so that's not changing. So we could say that now we have negative BA d dt cosine theta. And we're going to let theta be omega t. So we can rewrite that as BA d dt cosine omega t, substituting for theta. And then we'll take the derivative. So let's see, that'll get rid of our negative sign. So now I have BA omega sine of omega t. And then if we were to change that for n number of loops, for n loops, not Fruit Loops, n loops. That was dumb. I'm just going to shut up now. So for n number of loops, we're just going to multiply that by n. Okay, so our induced voltage is going to be NBA, NBA, what do you know, times omega times the sine of omega t. So you can see it's a sinusoidally varying potential difference. So that gives us the graph that you see above. And this entire thing out front, NBA omega, is going to give us the maximum, we'll say E max, or the amplitude. Don't have enough room to write amplitude. So it's based on the magnetic field that's already there, the area of the coil, the number of coils, and how fast you rotate it. So faster rotation is going to give us stronger potential difference peaks. We are going to revisit that equation in the next chapter, where we actually discuss alternating current some. What you need to take away from this is that we know the techniques behind generating alternating current, okay? Let me say two more things. First of all, go back a slide. Oh, you have to go back a slide. You have to go back a file. One thing I forgot to tell you about this, like in addition to airplanes, where this is happening, Have you ever had, I don't know, one of those, like a survival flashlight perhaps, and maybe it has like a pump that you have to do to charge the battery and get it to light up at all? What's happening? Take it apart. You're going to find a magnet and a loop, and when you do that, you're changing the area. Essentially, with some additional circuitry, you're using that effect to create a charge, and either charge a capacitor or temporarily charge a battery, all right? So, I think that might come in handy around here one day. Let's hope it's no time real soon, but get an emergency flashlight. Use Faraday's law for that. Now we also know how we can generate alternating current using Faraday's law. And don't forget that this apparatus was something that we saw in not the last chapter, maybe 2 chapters ago, when we were talking about the electric motor and the torque due to forces on a current-carrying wire. It's the same thing as an electric generator, just in reverse. So instead of supplying the mechanical input and turning it manually somehow, we already have electricity and we input an alternating current. And when that happens, we can get mechanical output. There's something really beautiful about exactly the same apparatus being able to use mechanically or to generate electricity. Like, there's a nice symmetry in that. But also, it's a really handy symmetry in electric cars as well, because the exact same apparatus, depending on what type of motion you're doing, can be used to take energy from the battery and drive the wheels, or if you're braking, you can use that exact same thing to push current or generate an induced current and drive charge back to the battery and recharge it. So your motor is also your generator, which is kind of cool as well. So electric cars are symmetrically elegant. I like that. Electric generator and the electric motor, specifically focusing on the generator at this point because it's due to Faraday's law, just operating in a loop over and over and over and over again, that allows us to use this apparatus to generate electricity, generate alternating current. Used in reverse, in a previous chapter, we said that apparatus is an electric motor. What I need to do now, I don't know if that wave was for me or not. It could have been for anybody, but it was kind of right there. So we need to talk about some of the problems with this, some of the holdups, things that negate the effects just a little bit. And that's what we see on these next 2 slides, which are mostly blank, so I'm going to have to write a good bit to explain it. First of all is something known as back EMF. Back EMF. This is an effect that happens for the electric motor. This is specifically for the electric motor. On the other hand, if you want to help keep these things straight, counter torque is a concept that applies for the electric generator. Think of these as subtractive effects. They are partially canceling out or acting against the effects of creating mechanical motion through a motor or electricity generation through the generator. So let me go back to the previous slide. So let's say, back to here for the motor. There we go. And take a look at this diagram once again. As far as we're concerned so far, it's like, well, you get this torque that's caused by a force because there's a current passing through a wire, and then we flip the direction of the electrical input so it sort of like pushes it halfway and then pushes it halfway again, and it just keeps pushing it and pushing it and pushing it and pushing it. And you might get the idea that like this could just be an indefinitely accelerating thing, that it just keeps going faster and faster and faster, that nothing's holding it up. Back EMF is something that's going to work against it just a little bit. So, based on the direction of those forces, the way they've drawn this is that the current is going around this direction. So we're starting with a counterclockwise current that we're driving through the loop that's in the magnetic field, and that's going to give us a mechanical output. It's going to make the loop turn due to torque. Think of what's happening due to Faraday's law, on the other hand. So while we're putting this in, think about the loop maybe, first of all, in a flat orientation. So tilt it back away from you just a little bit, and let's start at that point. And then let it begin to turn towards you. As that happens, there is flux toward the south pole that's increasing. Lenz's law says it's going to oppose that, which means it's going to generate an induced magnetic field the opposite direction which we could interpret as being a current that's trying to go the other way. Do we need to step through that again? Yeah, maybe, okay. Start with the loop flat so that it's directly parallel to the magnetic field lines, and then let it rotate this way. As it rotates this way, more and more of those magnetic field lines that are pointing toward the South Pole are getting in, which means that it's going to oppose that increase in flux by generating an induced magnetic field back toward the North Pole, trying to cancel out the increase. Going back that direction indicates that we're trying to set up an induced current that's clockwise instead of counterclockwise. That's going to be a subtractive effect, which means we're not able to put in as much current perhaps as we want to. It's subtracting some of it out a little bit. Let's make a couple of notes on that. So let's say in the diagram, we are inputting counterclockwise current. And then we're going to have an increase in magnetic flux that's pointing toward the South Pole. That is going to, according to Lenz's law, create an induced magnetic field that's toward the North Pole. Okay? And from that, we're going to have an induced current that's clockwise. It's not going to be as strong as what we're inputting, but it's subtracting from it some. Well, that's two different things. CCW is counterclockwise, I is current. Sorry, abbreviations. Trying to talk and write at the same time. Counterclockwise current. You could interpret this clockwise induced current as being because of a back EMF or a potential difference that's in the opposite direction than what I'm putting in. And that's always going to be there and have a subtractive effect. So a couple of other points about this. If we didn't, let me check back once again. Electric motor. If there was no load, in other words, if we weren't trying to use the electric motor to do anything and it was like a really light loop of wire and it's just spinning and spinning and spinning and spinning, what's essentially going to happen is that it's going to go faster and faster until my input is completely matched by the back EMF. Keep in mind, according to Lenz's law, it's about the rate of change of magnetic flux. So as it spins faster, it's changing faster, which means I'm going to get more backwards current or back EMF. Okay? So if there is no load, we could say that omega will increase until the back EMF equals my input EMF. Things would balance out, and it can't go any faster at that point. That is angular velocity, little omega.
And I'm sorry, why do you have back EMF at the bottom there? Isn't what we're describing back there?
For which part?
So you have a Lenz's law.
Mm-hmm.
So you have Lenz's law, induced current clockwise, and then you have back EMF. Why do you have back EMF at the bottom there?
If I have a current, it's because there's a potential difference. This particular current is coming from what we call the EMF that's backwards, in the opposite direction. Yeah. Anyone else? Yeah. It increases with angular velocity because of that. As the rate of change is higher, the induced voltage is increasing. And everything in here is the induced voltage. Yeah.
When we were doing that original, when we were talking about the torques on
Mm-hmm.
the wire, did we say that it would go, before like we talked about brushes to fix that, did we say that it would just go, like if it was flat, right, and then it would turn like that, vertical, would it stay at that vertical, or would it flip 180 degrees?
It's
First time on that?
it's going to end up aligned with the magnetic field. So the position where there's zero force, that's going to be, if it started like this, and the magnetic field is this way, it'll go that far. If it started maybe over here somewhere and I give it an initial spin, maybe it makes it all the way to that side. But it's going to end up aligning with the magnetic field.
Right, so it's just going to go 90 degrees until it's,
Yeah.
like roughly until it meets up with that.
So what might actually happen, it's going to have some momentum, so it's not just going to go boom and stop. It might swing past it a little bit, and then the forces will reverse, and it might oscillate a little bit and then get stuck.
We have the brushes there, and then
Yeah.
if it swings a little bit past, then it's going to...
Then it gets another push the other direction. Yep. Anyone else? No? Okay. So, if on the other hand there is a load, in other words, we're putting some resistance, some mechanical resistance, if you want to think about it that way. Maybe it's a tire, okay? It's something that is actually having to turn. This will limit the angular velocity, so it's only going to be able to go so high because, like, it's trying to actually turn something that has some mass and some weight, some moment of inertia, and that will keep the back EMF less than the input EMF. Okay? So if there's nothing there for it to try to turn, we're going to end up with this balanced case. It'll go as fast as it possibly can until the back EMF stops it. On the other hand, if there is a load, then it's never going to get to that limiting fact, and we're always going to be putting in more than is being subtracted back out. Okay? That is the back EMF concept. Counter torque is the exact same. It's just exactly backwards, just like the motor and the generator are really exactly the same, just operating in reverse. So in this case, we know that a generator is producing some current in itself because we're doing the mechanical input, and as soon as it starts spinning in the magnetic field, flux is changing, that generates a current. So the generator creates a current, and as soon as I have a current, that's going to feel a force. So all of these things we've been talking about this chapter and the last two are sort of interoperating at this point. So as soon as the generator begins working by spinning in the magnetic field, there is current in the wire, and that wire is in a magnetic field. It's going to feel a force, and it turns out that that magnetic force generates a torque that is opposite to the input. And you can do the exact thing with the right-hand rule back on the previous 2 slides ago if you want to, and you'll see that the forces are working backwards. So once again, as it goes faster and generates more current, we can say that there is more counter torque. Which I think makes sense, right? If you're spinning this manually, let's say, and it's like, ooh, I want to generate more current. I want to get more out of this. It shouldn't be the exact same difficulty. Like it's like, oh, okay, I'm just going to spin it a little faster. It didn't take any more effort in the process of generating it. Instead, if I want to get more, I need to put more effort in. So it makes sense that it's going to oppose me more the more I try to generate current. It takes more work to get more output due to this additional counter torque. Okay? So back EMF, counter torque, same idea, just backwards. Questions, thoughts, right-hand rules? Yeah.
Can you show us kind of like what you did on the last diagram?
Okay.
Can you like kind of show what that would look like?
Yeah, let's do that. So we'll go back there, and then woo, back there, and then wee, over to here. Okay? So let's see. We are spinning this which way? Let's do the same thing. It's, again, going to rotate from flat and come this direction. So we need to start by figuring out which direction current is going to flow because of that motion. So if that happens, we're going to generate, from Lenz's law, a clockwise current. Okay? Everybody all right with that? So we're going to start here with current that is clockwise. and that is the induced current because I'm mechanically spinning it for the exact same reasons why we had back EMF before, okay? Once we do that, well, take a look at, let's say, the wire right there at the top next to the North Pole where I drew the current. If current is going that direction and the magnetic field is toward the South Pole, notice my thumb is pointing sort of like perpendicular to this down that way. And that is an opposite direction from the way I'm trying to turn it, right? That's going to create a backwards torque. So you could look at the current in the other wire as well, and you would see that it has a force that's going up that direction. It's trying to oppose me. Yes? Yeah, it should be. Yeah. Just a lower amplitude in general. No voltage between the two terminals? I think it's not canceling completely because of even if it's in phase, right? You have a large amplitude on one side and a smaller amplitude the opposite direction that's negative. So it's going to overall decrease once I superpose those two waves. But there's still an output overall. It's not a perfect cancellation. Let's see, which one are we talking about here? The back EMF? It's because I control the input. So one is like an active effect, like I'm putting in a potential difference, trying to generate a current. And then Lenz's law and Faraday's law is sort of it's a secondary effect that's disconnected from what I'm putting in, and it's not going to generate as much. I see a nod down here. You agree? Yeah, they are separated from each other. And I can always turn the input up higher, but the Faraday's law is a separate effect completely from what I'm applying. What good is that equation? Which one on the top right? This is a limiting case. This only happens if essentially you're approaching zero moment of inertia that you're trying to drive. So are you ever actually going to get to that? No, but that's the asymptotic limit. Okay. Anyone else? Okay, we've got a third one of these, and maybe this is the most interesting of the three, and also we'll have to work through several steps to end up seeing what the effect is. So, eddy currents. You can think of this as happening really in any conductor that's either moving through a magnetic field or has changing magnetic flux through it. We're going to look at one specific case of a conductor moving through a specific magnetic field to give you a feel for how it works, but keep in mind it could happen in any conductor moving through a magnetic field. So, over on the right, we have a metal wheel. And for whatever reason, there's a magnetic field that only is near the bottom region of that wheel. So we're creating this magnetic field that only passes through this circle at the bottom. But you can imagine this wheel is going to turn, and different parts of the wheel are going to be passing through that magnetic field as it turns. Good so far? Okay. So I have a conductor moving through a magnetic field, and we're going to take a look at how eddy currents are created. So if we use conventional current, let's start by imagining that there are positive charges that are in here, in the metal itself, and they are essentially, at least right at the bottom, moving to the right with some velocity. Okay? A better way of thinking about it is they're moving, of course, along a circle, but right at the bottom they are moving to the right with a velocity. The magnetic field it's passing through is into the screen, so which direction do those positive charges feel a force? Well, V is that way, magnetic field is into the board, so the force is up, all right? So as they pass through, we can say, first of all, they experience a force that direction. Forces on moving charges. So let's make that number one in our list. We could say that the positive charges are moving with a velocity to the right, roughly speaking, and feel magnetic force up. Okay, moving to the right and feel a force up. That's our starting point, all right? If you look down at the bottom, you can see that they've drawn at least the first part of that. Look at the arrows that we see here, and you can see that all of those arrows are pointing up to indicate the direction of the force on positive charges. Step one, you happy? Okay, maybe not happy. Step one, are you satisfied? Step one, are you not angry? Can't even give me that? Really? You're really done with this semester, aren't you? A little bit? Not yet? Yeah, but mentally, kind of, sort of done. It's like you've learned all you can learn at this point. I understand, but just a little longer. We're almost there. We're going to make it. Number two. Can't write with a pointer, though. There we go. Number two. Take a look at the bottom figure, and you can see that the several points have been labeled. First of all, point C is part of the metal that's just outside the magnetic field, and in the next instant, it's going to move into the magnetic field. All right, so we're going to focus on that point and think about that region of the conductor and what it's experiencing. So at that instant that's currently drawn, it's not feeling any magnetic field. There is no flux. As it moves to the right and enters the field, it's going to experience growing magnetic flux that's into the screen through that piece of metal. It's going to oppose that, right? So you can imagine that little piece of metal is trying to oppose the increase by creating an induced magnetic field the other way, which is going to result in a counterclockwise direction of those charges. Okay? Let's write all that down. So point C in the metal, which is moving into the magnetic field. And two things are going to happen. First of all, according to Lenz's law, we could say that there will be an induced magnetic field that's trying to oppose the increasing flux that's going to point out of the screen, and that leads to an induced current that is counterclockwise in that little region. And you see those little current loops that they've drawn there, which is indicating they initially feel a force that's up, and then due to Faraday's law and Lenz's law, they start to feel sort of a counterclockwise force, right? We can do the same thing for point D. Notice point D is currently in the magnetic field and it's going to leave, which means you're going to get the exact opposite effect. So it's experiencing magnetic flux into the screen. It's going to lose that as it moves from D to E, which means it's going to generate magnetic field into the screen, which indicates that any positive charge there is going to feel a clockwise direction of current. So it initially gets pushed up, and then Faraday's law makes it move in a circle. Okay? So we could say D is moving out of the magnetic field. So once again, Lenz's law, we have a B induced that is into the screen, which is going to give me I induced, which is clockwise. These little induced currents in the region of the metal that's passing through a magnetic field are what we call eddy currents. But there's a step 3. Let me see if you have a question about what's happening there with the different forces. Anybody? Anything? Question? E is just representing a piece of metal that just arrived from point D. So why they didn't have like a, C and a D on the left to indicate it's going from C to D, from out to in, like they did on the right, I don't know. But it's just there to indicate where D is heading. All right, number 3. What is the effect of these eddy currents, the overall effect of these eddy currents? Keep in mind, if I have a current, it's going to feel a force if it's in the magnetic field, right? So we could say that I induce in the magnetic field feels a magnetic force. What is the direction of that force? I'll let you solve this one as practice. And we're specifically focused on these upward currents that are in the magnetic field. The ones that are down, they are not in a magnetic field. They don't feel a magnetic force. There's an answer staring you right there in the face, isn't it? But can you agree with it from the right-hand rule? They're going that way. Magnetic field is away from you. Force should be to the left. Okay? Up, away, left. Up, away, left. It's also a fun way to wave to people. I don't, it feels, it's kind of like get out, right? It's like, hi, now get out. I don't know. I don't know. I'm not going to start using that. So it feels a force that's to the left. Notice that opposes the direction that the metal is spinning. That's an opposing force. So this opposes the rotation. Which means this is one of those cases where an effect is happening. Maybe you need the effect to happen for an application. Maybe you want to try to avoid it as much as possible because it's hurting whatever you're trying to do with the spinning metal. So you have to be aware that something like this is going on and think about maybe some pros and cons. I'm going to say uses, which maybe these are the pros. And then over here we'll say issues. So first of all, this could be used as a braking device. You might imagine maybe a train with metal rims that are on the track. You could turn on an electromagnet that's passing through the wheel at the bottom. And then without having any braking pads, you could use that electromagnetism to generate eddy currents, which exerts a force against the rotation, and you could slow the wheels down. So if maybe not the primary braking, you could use this as a secondary braking instrument, or maybe use both of them in conjunction, depending on how strong those eddy currents are. Okay? So that's one option. Number two, you've probably all experienced this in metal detectors, which has a few different things going on. As you walk through the metal detector, there are pulsing magnetic fields that are being generated from top to bottom across your body, and they're oscillating really, really quick. Just think of them as turning on and off maybe 1,000 times a second. So a lot of magnetic fields are being created. If you're carrying any metal on you, well, what's happening? That's essentially metal that's moving through a magnetic field, which means eddy currents will be set up in the metal if it's there. And with the magnetic field that's being generated being turned on and off, it takes a second for those eddy currents to stop again. So there's a bit of a delay. So you can imagine magnetic field comes on, creates the eddy current, and then during the off state, it's making a measurement, making a reading. If there are eddy currents, well, currents create magnetic fields. So in other words, if any magnetic fields are coming off of you during the phases when the current's off, it's detecting that's being created in any metal that's on you, and then that's detected and beeps, and then you get frisked and kept off the plane, and all the bad things happen, right? Okay? So two different applications, one that you've maybe experienced, one that you haven't, that are dealing with eddy currents, all right? Keep in mind that there's problems as well. If there is a current that's flowing through a piece of metal, this is going to generate heat. And that can cause energy loss, depending on what you're trying to do. It's basically an energy leak in the system. So you would have to consider ways to try to cut down on eddy currents. One way to do this is, depending on how large these eddy current loops are, is that you could create your metal wheel maybe in segments with little bits of insulator in between. And then the currents try to flow, and they're just well, I can't go any farther. And then the effect sort of dies, okay? So that would be one method, perhaps, to cut down on the eddy current loops and keep energy in the system, all right? Questions about either or any of these three things? Anybody? Anything? Yes? The force is creating a torque in the opposite direction. Yeah. So if you wanted to think about this particular force, it's a distance from the axis of rotation. It's trying to spin it the opposite way. So it's essentially a slowing down, a braking effect on a wheel. Yeah.
If I created a magnetic field with an actual current magnet, would that current magnet field work as well?
Yeah, Newton's third law says that it would have to. Yeah. I feel like you're having ideas. You're going to go home and play. Yeah.
Is that strong enough to slow down a train?
Yeah.
Maybe?
Yeah.
Would you have to have how many Teslas is that?
I think you're going to create a really strong electromagnet that's passing through the wheels that you could create in the rails themselves. Magnetic field strength, I don't know, I'd have to look that up. Is it worth it? Hard to say. But if nothing else, it doesn't involve moving parts that are going to rub against each other and wear out. So it's an overall cleaner process. So, yeah. The C and the D, they are both under point 2. They're just trying to indicate certain regions of the metal that we're discussing. So point C just indicates a little piece of metal that's right in this area that's about to enter the magnetic field. D is a little piece that's in the magnetic field and about to leave it. Anyone else? Yes. Oh, can I talk about it? Yeah. Yeah, so if instead of spinning, if we could have an oscillating magnetic field in that particular region through a stationary wheel, that would serve to actually turn the wheel, perhaps in the opposite direction. I'm not sure what the use of that would be, but it's the same concept overall. It's just we're keeping the metal constant in position and changing the other thing, but the effects are exactly the same. Anybody working on the survey right now? Just curious. No? Nobody? You forgot about it, didn't you? Question. I wouldn't relate that force to the C and the D. Rather, connect the force to these currents that are going upwards in that part of the metal. So I guess you could say that D has a little current that's up and it's feeling a force, but C doesn't because it's outside the magnetic field. This is good. Good questions. One more. Ooh. I don't see why not. You have charges that are available. I don't see why not. So, can I confess something to all of you? These 2 slides, I was like, 10 minutes tops. Yeah, that didn't work out, did it? 35 minutes in, we've covered these 2 slides. That's good, though. We'll be okay. Let's see. So, we've got transformers to talk about, which isn't terribly difficult, and a couple of conceptual questions related to that. And then a little bit of theory, which you can see has some asterisks next to it, because we're not going to do a lot with this, but it'll show a more extended version of Faraday's law that will come back to haunt us maybe in chapter 31. And then we're going to listen to this guy sing for a little bit. Wow. I don't know. Sad overall. And then we'll be done with this chapter, and we'll see what time that gets us to. Okay? So before we do that, I've got something I want to show you. It takes about 15 seconds. And I want to show you that I just stumbled into this the other night. You know, it's one of those things, you're just scrolling through Facebook, and it's like, what's this? And you watch, and all of a sudden I saw that this animal really, really agrees with me. So I'm going to have some watermelon. Apparently it's crunchy. Mm-hmm. But, right. So as you can see, if you think I'm an idiot, you can't disagree with a cute animal like that, right? Yeah. I think he nailed it. Stonky feet. That's it exactly. Oh. So let's talk about transformers. Transformers? No, maybe a different transformers. This is simply an electrical device that is used to convert between different voltages. And it is basically just a system of ratios. There's nothing mathematically difficult here. I just want to quickly set up the equations for you, explain what its purpose is and where it's used, and then we will move on. It's going to be another application of Faraday's law, which means that for this to work, we have to have changing magnetic fields and changing magnetic flux, or nothing happens. Which means when we're talking about different voltages, this is going to be used with AC voltages. If I have alternating current, that's going to allow Faraday's law to take effect. But I should put a little subnote on here. In general, DC won't work. But although we could say something like a DC pulse can cause a brief effect. If you think of a DC pulse that's like, turn on some current, turn it off. Well, that's a change in current, which causes change in magnetic field, change in magnetic flux, and you could get something to happen, but it's just for an instant. If I have alternating current and therefore alternating voltages, this is something that's just going to keep operating because the magnetic flux is ever changing, never stops changing. So let's take a look at this sort of blown up description of a transformer. You will notice on the left we have one circuit, the primary circuit, which is an AC source connected to a loop of wire which has N loops. We call this the primary circuit. So the AC source is going to input the primary voltage, we call it, and that voltage is going to be applied across that N number of loops. Nearby, and typically really close nearby, if not sort of nested inside of each other, we have another circuit, a secondary circuit. There is no electrical connection between the two, so don't make the mistake of thinking that like rectangle of iron there is like something that can conduct. Instead, it's fully insulated from that, and no current can pass through it. Instead, we're going to use it to help direct the magnetic flux in just a second. So the secondary circuit is not connected, which means that there's nothing there that's creating voltage. The only voltage is going to come from Faraday's law. It's going to be an induced voltage that happens in the secondary circuit. And you can see they've drawn it with a different number of loops or coils, and we're going to use subscript S to indicate the number of loops and the voltage that's output. So let's start on this side. And we're going to focus on what we might call the input side of this, the input or the primary. And we're just going to apply Faraday's law, essentially. Okay, so we could say, first of all, that the primary voltage, and let's just focus on the magnitudes because that negative sign is just Lenz's law, is going to be the number of loops in the primary circuit times the rate of change of magnetic flux. So here, think of this as we are causing this voltage to happen and to oscillate, and it is generating a change in flux through the loops of its coil. All right? So this isn't using Faraday's law backwards. Instead of saying, ooh, flux is changing and I get a voltage, it's like we're doing the voltage and it's creating a changing flux through that particular coil of wire. Right? On the other side, in the secondary circuit, or the output, we're going to use Faraday's law once again. So V sub S is going to be equal to its number of loops times the rate of change of flux through it. So this time, it's experiencing this, and it's going to generate the output voltage. Here's the key. These two things, this rate of change of flux is set up so that these are the same. And you might look at the diagram and be like, I'm not buying it. Well, keep in mind this is sort of an exploded diagram. Things are going to be much, much tighter in an actual transformer. And the flux is sort of directed and concentrated in the iron. We're dealing with a ferromagnetic material, meaning that if the ferromagnet is experiencing, we'll say, a magnetic field in this direction, and you could imagine that, it's going to kind of go out like this in both of these directions, there's going to be a much, much stronger magnetic field in the iron than in the air around it because of the ferromagnetic effect. Well, just look at the way like these lines are sort of bending. You can imagine that they're going to wrap back around this direction, which would be sort of down through the other coil. And again, pretend these coils are really, really close together and the ferromagnet is magnifying the effect. Overall, what's going to happen is that whatever flux is being created in the center of this is really, really close to the same as what's going the opposite direction in the really close nearby coil, which allows me to connect these two equations. Keep in mind, is it quite that perfect? No, that's okay, all right? It still helps us get the concept. There's going to be some losses there. This might be to sort of like take the two and overlap them. You could insulate them in some way so that one coil is inside the other, and then they're literally experiencing the exact same flux. But hopefully this diagram will give us the basic idea. If the rate of change of flux for those two is the same, we could merge those two equations together into one, and you're going to get something that looks like this. Ooh, let's go up here. The voltage in the primary is equal to the number of loops in the primary times the voltage in the secondary divided by the number of loops in the secondary. And then you can make one last change to get the voltages all on one side and the number of loops on the other side. And we simply have two ratios. The ratios of the two voltages, the one that I'm putting in and the one that I'm getting out, is going to be the same as the ratio of the two number of loops. So in other words, if the secondary coil has fewer loops than the first one, we're going to get less output voltage than what I put in. It's a means to take the voltage from some high level down to a lower level. If we were to reverse it from what's drawn in this diagram and, just flip the two circuits so that we were going from a case where I had a smaller number of loops to a larger number, you're going to get more output voltage than what you put in. So you're going to have a step-up situation. So let's just make a couple of notes about this. We could say that if you have more loops in the secondary, then this would be a step-up transformer. And if I have fewer loops in the secondary, we would call that a step-down transformer. And I've run out of room, but there's more that I want to put here. So as you can see, equation-wise, there's not a whole lot to do with it. It's all coming straight out of Faraday's law, though. But you might be thinking, wait a minute, so I can just get more voltage just by having more loops of wire? That feels like I'm breaking some sort of conservation principles, and you can't get something for nothing. So let me go and add one more slide here on the next page and make a point about this. What does change? Something for nothing. What do I have to pay in terms of getting more voltage? So what we do have to say is that the power that we put in is going to equal the power we get out. Again, we're assuming a perfect situation where there's not some small losses due to non-conservative forces. Power in terms of voltage and current could be written as I times V. So we'll say that IN times VN is going to be equal to I out times V out. Or if you wanted to write that in terms of what we called the coils, that would be I in the primary times V in the primary is equal to I secondary times V secondary. And if you rearrange that equation, you are going to get IS over IP is equal to VP over VS. Notice this time secondary and primary are flipped on the other side. Meaning, if I step up in voltage, I'm simultaneously stepping down in current. So I pay for it in current. If I want the voltage to go up, there's going to be less current. And if you wanted to merge these two equations together, we could say also that this is going to be equal to NP over NS. And then we've got everything combined in one. So where does this come in handy? A couple of things. First of all, electric power transmission. If we want to get electricity from where it's generated to where we want to use it, say in our home, well, it turns out that often that is over many, 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 many miles. And if you think about passing that through miles of cables, even if they have a really, really low resistance, well, that resistance adds up as the wires get longer and longer. If I just say, like, ooh, someone over there is going to need 10 amps, let's just send them 10 amps. That 10 amps has to flow for miles and miles and miles. It's going to pass through all that resistance. The wires are going to heat up, and I'm going to lose a lot of energy in the process. On the other hand, if I step up in voltage and drop the current, I can transmit a high voltage, low current signal on the other hand, and then since the current's low, I'm not going to lose as much in the transmission over those many miles, and then sort of do the exact opposite when it gets to the end and drop the voltage, which will increase the current to what I need it to be. So we have less power losses by using a transformer, a step-up and a step-down transformer on either end of the power transmission. So, those big, huge power things that you see somewhere around the city where there's like big cylinders everywhere, that's probably either a major step-up or step-down transformer that looks something kind of like this or this. An electric substation. Out near the buildings, you often on a pole see like a smaller cylinder, which is another level of stepping down in transformer to get the voltage down until it gets to your house to the voltage you needed at the wall, which is typically 120 volts. Often from there, that's not low enough for many of the things we want to do. So someone's probably got a cell phone charger like right there, and you could just hold it up right now, but you don't have to. There's a little box on there, right? Like it's never just like, ooh, plug it into the wall and just plug it into my phone. Like the wall thing always has a box. There we go. If you take it apart, I should just say, you got it out, take it apart. You will find a transformer in there, and it's a step-down transformer to go from 120 volts typically to something on the order of 5, just depending on, now we have fast chargers, which are a little bit higher in voltage. If you were to try to just be like, oh, well, why do I need this wire? I think I'm just going to take some copper and connect my phone to the outlet. That should work to charge it. You're going to blow your phone up because the voltage is still too high. You need another step-down transformer to get it for the particular electronic that you're trying to do. And you have a face like you know someone has tried this. No? Okay. Not, oh, no. Please. The people are going to die, aren't you? Please don't do this. Question. I'm sorry? And not just a big resistor. Big resistor is more energy losses. If I pass that current through a resistor, it's just a lossy system that heats up. So it's a cleaner way to transmit what I need for the phone. Okay? How about a couple of questions? Don't think about these too long. They're not terribly hard. And also, look at these wires. Look at those. Man. Someone put a lot of time into that. And also, those loops don't even complete. So I don't think anything should happen in this diagram. Everything there is broken. You'll notice there are 2 loops, and then 4, and then 4, and then 2. So just due to ratios, I'm stepping up and then back down to the exact same voltage. So the light bulb should get 120, okay? In our next slide, we start with 120. We're going to go to 240 and then to 120. and they tell us that it's 1 amp in the middle. And I know that when the voltage goes up, the current goes down. So what do you think the current is at the beginning and at the end? Yeah. Lower voltage means higher current, and everything is just a direct ratio. So we're going to have 2 amps of current at the start and at the end. And then finally, what about this one? They're trying to trick you. That's a battery. It's DC. Nothing's going to happen. So, 0. Yeah, it's just wrong, isn't it? Yeah, it doesn't work with direct current. It's a 6-volt battery. So that's the end of that. Any questions about those 3? Anybody? Anything? Yeah.
Not about those 3, but about like lower power losses.
Yep.
So power is V squared over R. So wouldn't a higher voltage be a higher? There's also I squared R, so a lower current.
Yeah. There seems to be a contradiction there, right? If you work through the numbers, things should work out so that the I squared R would be a bigger loss than the V squared over R. But I'll leave you to those details. I see cheering in the back for something. I don't know what y'all are clapping for, but you're like, yay, it's 3 o'clock. Who in the world knows? Yes. Previous post-lecture, I have not uploaded those yet. I will do that soon. Good reminder. Thank you. All right, so here's where we stand. There is 2 slides left in chapter 29. Just 2. We're going to cover those. And then in chapter 30, I want to do the first slide. That's what we're going to cover today. That'll put us in a really good place as we go into next week. Okay? Now, I think that those are about 10 minutes long, but based on what we've had so far, I sorely misjudge how long these things take, so it may take the rest of the regular class time. Who knows? So let's do this one, and let me point out that there is a more general form of Faraday's law. And after you see it, perhaps you can make the connection back to the version of Faraday's law we've been using. So on the right side of the equation, we still have the negative sign. You could have the in there if you wanted to, but we're going to leave that out. And the rate of change of magnetic flux. On the left is a potential difference. We have another way to write potential difference that's in terms of the electric field. So on the other side, we could write this as the closed integral of E dot dl, which remember, that's just a potential difference, okay? So we're connecting the changing magnetic flux to electric fields. And if you think about it, well, if I have an induced current and an induced potential, none of that can happen unless there's an electric field there as well. So what we didn't say is that this creates an induced electric field, which allows us to connect to some of those earlier, more theoretical chapters. And let me show you a little bit about how this works by using the example that you see on the left. And this is not a terribly hard example, and very quickly you can see how this equation works and get a feel for it. So the diagrams, on the other hand, are a little bit confusing. So what we're going to say is that we have 2 circular magnets. So imagine that here I'm looking down on the circular pole of a magnet, and we're going to put it very close to the south pole of another circular magnet. So if you wanted to look at it from the side, it would look something like this. I've got a circular end to one magnet and a circular end to the other magnet, and we're going to put their north and south pole very close to each other. Okay? So I have this directed magnetic field that's going to point from the north to the south pole in this little region between the 2 ends of the magnets. Good so far? Okay? So if we were to sort of go into that region and look down on the north pole of that bottom magnet, this is what we would see. We would see a magnetic field that's pointing directly up toward us. Okay? Everywhere in this circular region. So what we're going to do is use this general form of Faraday's law to find the electric field in that region between the two magnets, okay? So let's start the process here. We're going to say that we're going to find E for R less than R naught in that particular diagram. And you can see they've already drawn a path for us there that's got a radius R that's less than R naught. So integral E dot dl is equal to, and let's do magnitude only and leave out that negative sign. It just gets in the way. Like so. As long as I'm at a constant distance, the electric field is going to be a constant value, and you can see that it points around the circle tangent to it as they've drawn it. So we're going to have E times the integral dl, which is just going to be the circumference. So this is going to be E times 2 pi r on the left-hand side. On the right-hand side, let's plug in our equation for flux, which is BA cosine theta. And everything is perpendicular here, so that's going to, not 0, going to go to 1. Otherwise, our problem was over. The area is the same, and we're going to say that the magnetic field is changing. Notice up here in the caption, it says that B is increasing. So somehow we're able to vary this magnetic field, and we're ramping up the strength of the magnetic field. Ramping up the strength of the magnetic field means that in that region between the two magnets, magnetic flux is changing. So even if we consider a theoretical region where there's not actually a loop, if we consider this theoretical loop, flux is changing through that region, which means we're going to get an induced voltage, induced magnetic field, induced electric field. All of that stuff is still going to happen. The only thing that's not going to happen is an induced current because there's no wire there. There's no place for it to for charges to flow because we're simply in free space. So on the right-hand side, dB dt, we're going to leave that around and just solve this for the electric field, and you're going to get, well, that's, I skipped a step. Let's put in something for A first. So A is pi r squared. And then we can solve for E. So the pi is gone, one of these r's is gone, and then we've got r over 2 times the rate of change of the magnetic field. So r, it depends on how far you are from the center of the magnetic field region, and it depends on the rate that the magnetic field is changing. Notice it's linear with respect to r. So as I get farther and farther from the center of the magnetic field region, the electric field is just increasing linearly up to the end of the circle, all right? Because it's just proportional to r. If we wanted to step outside and go a little further and look at the electric field outside of that region, it's really essentially the exact same thing, and I think I have just enough space here somewhere to do it. Let's do this. Ooh, you're like, that's not enough space. You want to bet? Oh, that's plenty of space. Look at all that room. That's fantastic. Now I just have to make this smaller, and then everything will fit. So we'll do the exact same thing. What about R greater than R naught? We'll do the same. So I've got E 2 pi R on the left-hand side once again. And on the right-hand side, we're going to have pi r naught squared dB dt. Because the A is about the area that we're including that has the magnetic field changing within it. Well, that's everything at this point. We're including all of that. So let's see. The pi cancels, and that looks like it's all that cancels. So E in this particular case is just going to be r naught squared over 2r dB dt. Notice now r naught is a constant. It's proportional to 1 over r. So as I get outside of that region of space where there's a changing magnetic field, well, the electric field is going to be dying off, and you can see that if you zoom out on the diagram there in the bottom middle, proportional to 1 over r. A theoretical look at Faraday's law, all right? So we did a lot of practical things throughout the chapter. This is going to fit into chapter 31 when we finally look at Maxwell's equations. We'll see this general form of Faraday's law once again. I think that's about all I want to say about that slide. Any questions, thoughts, complaints, anything? No? All right, so the last slide in this chapter, chapter 29, almost done. I really have a hard time looking at that guy. Wow. He's a little full of himself, don't you think? He's like, yes, I can sing, and I look good doing it, I guess. I don't know. But this is just terrible, all right? So 3 quick sort of everyday examples of Faraday's law of electromagnetic induction. A microphone. A microphone. I've got a microphone. Too bad it's tiny. We should take it apart and see what's inside. I bet we would find something that kind of looks like that. There's going to be a little magnet in there and a coil of wire. Okay? What is essentially happening in the case of a microphone is you can see that there is a very light cone that is connected to the loop, and this can move back and forth over the stationary magnet that's there. So if the sound waves come in, they vibrate that cone with a pattern that matches the incoming sound waves, and then, well, that coil of wire is going to move with small movements back and forth on the magnet, which means there's a changing flux that's happening with a very specific pattern. That changing flux is going to generate a current, and we can connect that to an amplifier and amplify the current and look at it, or play it back through loudspeakers, and it'll match the pattern in exactly the opposite way, okay? So there's one case. If you happen to play an electric guitar, it's kind of a similar idea. Part of the string is magnetized, and it's going to be moving near a coil of wire as it moves back and forth. It's basically the exact same idea. That magnet is changing the flux of the coil. It's generating an electrical signal that matches the vibrations of the string on the guitar. Or if maybe you swipe a credit card, which, can we please get rid of swiping credit cards? I'm just done with it. And the pen, the chip, that's too slow. Let's just end the whole thing. I think everything should be smartphone and smartwatch payments, and it's fast, it's simple, it's secure, and I'm just tired of being like, okay, which forms of payment do you accept? It's like there's a trickle-down effect. I always start, I'm like, can I try my watch? Watch works, great. If that didn't work, it's like I fall back to this. If that didn't work, I fall back to the card, and eventually you end up swiping, and all is lost, and I hate it. But anyway, you don't care, do you? I understand. So if you're swiping a credit card, the magnetic tape on the back of the card contains very specific magnetic fields, and if I swipe that near the reader has a coil of wire that's changing magnetic flux in a particular pattern through the coil of wire, which generates a specific current that now carries a signal that in some way matches the magnetic field that was originally imprinted on that magnetic tape. Okay? Faraday's law is everywhere. It is around us all the time, from tiny applications to bigger ones. Yeah? That is a good question. I would think that the magnetic field is it's simply storing a long-digit code in a way. I mean, as long as you have a certain number of digits, then all of a sudden there's ample possibilities. How do they create that magnetic field on there? That's an excellent question. I need to look into that. Anybody else? Yeah. On the string of the guitar? Is that what you said? Okay. There's just depends on what the string is made of. It says here that it's metal, but the magnetized part could be a little piece of ferromagnet or something that's either wrapped around that little portion of the string, and then, well, magnetized. You have a magnet that's there that's moving in relation to a coil. 29's done. Yay. We're done with 29? Yay. We've covered 17 through 29 at this point. Do you feel pretty good about that? That's not bad. Only 30 and 31 remain. That's it. 2 chapters, 2 classes. It seems like a lot, but both of them are short. Okay? So I think what we're going to do is say on Tuesday we're going to cover chapter 30, and on Thursday we're going to cover 31, and it'll be a nice clean ending. Sound good? All right. Farewell. Do the survey. I'll see you Tuesday. Goodbye. I don't think I have anything else to say. Goodbye. I'll say that again. Goodbye. 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 Thank you. Thank you. Someone said goodbye instead of ignoring me. As you leave, don't forget, take that with you. Let him haunt your nightmares.